Okay, I think we can go ahead and start the meeting. This is Fred Amendzadeh. Grant asked me to introduce the speaker today. So I'm pleased to introduce Masashi Ikuta, a manager at NEC Corporation. He is from the AI platform division based in Tokyo, and he is going to speak to us about the uses of HPC computing for subsurface applications. Just to make a note that Ikuta is located in Tokyo, and it's about 3 o'clock in the morning their time, so we appreciate his willingness to give this talk this early in the morning or late at night. Ikuta, go ahead.
President, thank you for the introduction. So, yeah, my name is Masashi Ikuta from NEC Corporation, a global IT company with its headquarters in Tokyo. So, yeah, so it's a great honor to deliver a presentation here today, and I would like to thank people who made this happen. So, it is actually 3 a.m. in the morning, but it's my great honor to talk here today. So I would like to talk about HPC, high performance computing, and AI, machine learning for subsurface applications. I will show you many examples from oil and gas vertical, but what I talk today will also apply to other applications like carbon storage or CO2 monitoring. And so that said, I would like to start from this slide that we presented at Rice University Oil and Gas HPC conference this month. I can give you a copy of that presentation if you want. So in that case, yeah, please contact me. Well, this slide illustrates how I understand the ENP value chain and role of high performance computing, artificial intelligence, and data analytics in each step. So of course, everything starts from measurements using sensors, and that will be followed by modeling and surface imaging, which is about so-called FWI, full wave inversion, and RTM, reverse time migration. And the challenge here is that these operations can move from matter of a few hours to even matter of few days. So it really is time consuming. But if we can do the operation much faster with the help of HPC, AI, machine learning, or mix of these, there would be a huge value added because we would be able to do things more seamless and make decisions faster or understand how things are moving forward more accurately. That means from all company point of view, you can improve success rate in exploration and reduce failure cost or delay cost. It means faster to revenue. So that's very important, and I think it's very worth investing here for all companies. Same is true for reservoir simulations. If we can do more reservoir simulations, then we can pick up the right one from larger ensemble of our simulation models by doing so-called the history matching. So you can increase recovery factor and thus increase revenues. And so again, it's very important, and it's again very time consuming. So basically what I'm trying to highlight here is that each step of this whole operation involves a lot of data and requires a lot of high performance computing. And today everything is connected to AI, machine learning, and it is a mix of high performance computing and AI, machine learning, and data analytics. But I often hear application performance have reached a plateau. It's been a while since people started to say Moore's law is coming to an end. And so, is this true? Well, if you look at this chart, you can see the number of transistors, the orange dots in the top. That is continuing to grow. But if you see the blue dots, we can understand that thread performance have reached a plateau. And we can see that the number of logical cores, the black dots in the bottom, it is increasing. So I understand the fact is that we are having more and more number of cores, but the performance of each core is not increasing anymore. That is the fact, I believe. And this reminds me what late Seymour Cray asked. The father of supercomputing asked, if you are plowing a field, which would you rather use? 2 strong oxen or 1,024 chickens? So fundamentally, he asked, do you want more and more cores? Can you handle it? Or in other words, can you use so many cores efficiently and gain performance out of it? That was his question. And I believe your answer depends on what kind of application you run. And Seymour Cray believed 2 oxen is more efficient in many cases. And that also applies for scientific computation, and that's why he designed and developed vector computers. So I think vector is going to be the key word in this talk today, but what is vector computer or vector processor? I think many people already know very well about vector, but some might not be so much familiar with vector. So let me try to explain what is vector using this rough sketch of general processor, or I might call it scalar processor, GPGPU. That is about NVIDIA GPU cards and vector processor. So a scalar processor or a general processor that can compute relatively small piece of data at one time. And nowadays, scalar processors have many cores in one processor. And it is in the middle, GPGPU. The GPGPU have massive number of cores or many sets of cores. They have a stronger set of cores than many of those. So they can compute more data at one time and output more results at one time. And in the right, you see vector processors. Vector processors can compute many elements, which is called vector, or people also call it arrays. So you can compute many vector by one instruction. So vector processors have very powerful core. So I sometimes call it big core or powerful core. And to load such large data to the powerful processor core, vector machines have large memory bandwidth. And as you know, it is often the case that vector or array is the core part of scientific computation, and thus vector is suited for scientific simulations. And I believe that applies to, well, oil and gas applications as well. But you might say, well, scalar processors have features called SIMD, single instruction multiple data. So what is the difference between SIMD and vector? I would say the data size is different. Of course, there is more different in details, but in a word, the data size is different. For example, in AVX512, which is the vector feature for X86 processors, you can handle 512 bits at one time. But in our energy vector computer, which I think is the only real vector machine available today in the market, it can process more than 16,000 bits at one operation. So it's 16 kilobits, 16K. So a real vector is sort of AVX 16K. So that is how I will call it. So I said NEC vector computer is the only real vector computer in the market today, and let me explain about it. So this is the architecture of SX-Aurora TSUBASA, which is the name of the machine. So when I say SX-Aurora TSUBASA, it is a vector host, in short we say VH, plus vector engine, in short I say VE. And vector engine is not standalone like GPGPUs. It is connected. It has to be connected to x86 server, which is called the vector host. And when it comes to the software, operating system is Linux. Programming language, you can use Fortran, C, C++, and Python as well. And I would like to highlight that you don't need special programming skills like CUDA or OpenACC. You just write Fortran or C or C++, and that's it. There is automatic vectorization compiler, which does the vectorization, parallelization, and other optimizations to deliver the high performance. And as for the interconnect, we support InfiniBand and vector engine to vector engine direct communication. That is also supported. This means that when a single vector engine card communicates to another vector engine card through InfiniBand, it doesn't have to go through the x86 vector host server. VH is not involved. So the thing is that programming is easy. You don't need special skills, and you can leave the compiler to do the vectorization and other optimization, and thus you can enjoy high performance with minimum effort. That is the story. So in this talk today, I will refer to some performance numbers, and actually vector engine has several SKUs. I'm not going into the details of the difference of each SKUs, but I want you to remember two SKUs. The two major SKUs, which are type 10B and type 20B. The difference is the frequency and the memory bandwidth, and the performance number that I show you today comes from these two SKUs. And here's a slide about software. The vector computer supports Fortran and C and C++. I just told you about this. There's NLCPy, which is similar to NumPy. I will come back to this later. OpenMP, MPI, various libraries, it's there. And we have this under tools, profilers, and we also have original profilers that can show vectorization information such as vector ratio, vector length, and so on. And I don't think I want to go into the details today, but something interesting would be hybrid programming. You can do offloading or even concurrent execution. There's many execution models supported in this vector machine. Okay. And I'm happy to tell you that vector computer is a proven technology. And we have many users around the globe, especially in Japan and in Europe. And here are some big users. So in the left top, you see NIFS. This is a national institute in Japan, and they started to use a 10 petaflops vector machine last year. And next to it is DWD, which is a weather agency in Germany. So in Germany today, they are doing climate simulations and daily weather forecasting using this vector computer. And I think this is a good example that vector computer is ready for mission critical usage as well. And we have many academic customers. This is because you can get good performance with minimum effort. Remember, I told you that you don't have to write CUDA or OpenACC. And this is good for students who don't want to spend their time in complicated programming. And finally, in the right bottom, I have JAMSTEC. You might remember the Earth simulator system, which was the #1 system in the past. And we just installed the 4th generation of the Earth simulator. So this is how it looks like. It is a hybrid system, which consists of vector cluster, x86 cluster, and GPGPU cluster. Well, the vector part is the largest part, but I believe hybrid system is going to be the trend from now on in the future. Because, there is various types of applications in the real world, and there is no processor that is good for everything. Each architecture or each processor has its sweet spot. And what becomes important is that to do things efficiently, you have to run the right application on the right architecture. So this kind of hybrid system, I think it's going to be the trend in the future. Okay, so let me also name some US users. The first one is Plano, Los Alamos National Laboratory. They decided to have our vector computer since they observe good performance for a range of HPC and AI applications. They were impressed that they can enjoy high performance with minimum porting efforts. And another one is NRL, US Naval Research Lab. They had many vector codes developed for the old Cray vector machines. And they didn't want to invest porting those codes to GPGPU or rewrite and optimize them for x86. But at the same time, they didn't want to throw them away. So likewise, the vector machine was the right solution for them. With minimum porting efforts, their vector code came back to life. And talking about oil and gas, we started engagement with Baker Hughes and DGB. They are currently going through the evaluation stage. Okay, so from this slide, I would like to focus on performance numbers. And the first one is about stencil performance. And as you might know, stencil calculation is a kernel part of seismic imaging, and the vector computer has its own stencil library. It is called SCA, Stencil Calculation Accelerator, and you can see that it is doing a very good job. The red bar is the vector machine using SCA, Stencil Accelerator. So compared to V100, NVIDIA V100, that is the GPGPU machine, you can see that in many cases, it's more than 2 times faster than the V100, which is shown in the green bars. And this is a seismic imaging application from an industry-leading oil company. So in these charts, higher is better, and performance is normalized by Skylake performance, which is shown in the gray bar. And as you can see in the left chart, the vector machine is in the red bar. That is showing 4.5 times better performance compared to the Intel Skylake, and also higher performance than the NVIDIA V100. So I have to say that Skylake is, well, pretty much old, but this is the performance that I got from the oil company. So I did nothing about the x86 and V100. The oil company did the tuning, and they just gave me the numbers. And what I did is the red bar. So this is what I have. The right chart is about performance per watt. Today, there is many discussion about power consumption, and many people do care about power consumption. So in the right chart, you can see that Vector has advantage in terms of performance per watt as well. It is more than 2.5 or nearly 3.5x compared to other architectures. And another thing interesting, this is something we were selected, and we actually presented at SEG last year. We did some joint studies with a company named NAG, Numerical Algorithm Group. We worked on a seismic application that NAG developed and compared our vector machine performance with Skylake and V100. So again, we did nothing about the Skylake and V100. The NAG group did it, and what we did is the vector part. So again, you can see the red bar is overwhelming other architecture depicted in green and blue bars. And this slide is performance related to reservoir simulation. We tested HYPRE. HYPRE is an open source software from Lawrence Livermore National Lab. And it is a library for scalable solution of linear systems. And as far as I understand, this is the counterpart of reservoir simulations. And HYPRE has many solvers, but here we picked up GMRES solvers. So I do have other results from other solvers as well. So if you're interested, please contact me. I think I can share it with you. But yeah, in this case, we tested with these data sets shown in the right part of this slide. I think these data sets are related to reservoir simulations, and this can be downloaded from the internet. So again, compared to AMD EPYC processors, Vector, which is shown in the orange bar, shows good performance. So in this chart, lower is better, and you can see the performance is nearly doubled. And this slide is about SpMV, sparse matrix vector product. And SpMV, that is one of the most important performance factors among various simulations, especially in CFD, and that also includes reservoir simulations. So it plays an essential role in solving large-scale linear equations using iterative methods. So this basic benchmark result implies that Vector has a good aptitude for such kind of calculations. And I do understand that SpMV, the performance is highly dependent on the choice of matrix data format. And here we use BBMAT. BBMAT is data set for geomechanical model for CO2 sequestration. So you can see the good performance of the vector machine. So the vector machines, you see 3 lines going up into the sky, which is scaling very well. So these 3 lines are the vector machines. And so you see the scalability, you see the absolute performance compared to other architectures. Now let's talk about AI and machine learning or big data. And everyone, every industry, every vertical is talking about AI, artificial intelligence. But the problem here is that AI is very broad. And I think it is better to make it more specific. So first of all, I would like to share a report from a third party named Cambridge Consultants. They did some studies and reported where vector architecture is good in AI and big data. They concluded that vector computers are good at the red dotted boxes, which are the statistical machine learning, graph analytics, database analytics, and deep reinforcement learnings. So on the other hand, the report says that GPGPU is good for CNN, DNN, and maybe RNN as well. So to make it more graphical, here is how I see the AI machine learning arena. So I think vector is good for statistical machine learning and data frame. And in terms of the framework, I think this is about scikit-learn and Apache Spark. And to this end, I have a middleware named Providis, which is compatible to scikit-learn and Apache Spark. And there is NLCPy, which is a NumPy-like library. There is MLP, multi-layer perceptron, LSTM, and CNN, convolutional neural network, down in the bottom. And so I have to say GPU is doing a very good job here, but I think that's for the case for pure or very simple CNN or LSTM or such kind of cases. And in any case, vector is better than CPU, although it might be behind GPU in some cases. But besides, I believe it is not only pure or simple CNN in many cases. In many cases, I think it is a mix of HPC and AI and machine learning. So we are working on this as well and have some projects going on related to TensorFlow and PyTorch. But yeah, I'm afraid I don't have much time to talk about this today, so let's talk about it in next opportunity. So here are some performance numbers from Forbes, which is the framework for the framework compatible to scikit-learn and Apache Spark. The left chart shows 3 examples from machine learning, which are logistic regression, k-means, and SVD, singular value decomposition. The right chart is DPCH benchmark results showing a data frame performance. So again, you can see the vector, the red bar, is doing a very good job. And so yeah, I forgot to mention, but the good thing about Frobet is that it is an open source project, and you can download from the GitHub link that is shown in the bottom of this slide. And another good thing about Frobet is that it also supports x86, and we often see good performance there as well. So I encourage everyone to have a try of this Frobet thing. So this is what algorithm Frobet supports. So basically, vector is good for large sparse data. That's my understanding, but Frobet supports both dense and sparse data. So apart from LR and k-means and SVD, we have word-to-vec, decision tree, graph algorithm, random forest, and so on and so on. And of course, this list is growing, and we will support more in the future. Now, talking about Python, as you know, NumPy is frequently used in AI and, of course, in scientific computation field as well. And that it would be nice to have sort of a NumPy accelerator. And that motivated us to develop NLCPy. So NLCPy is a NumPy-like library, and it is actually very easy to use. If you have a Python script using NumPy, you only need to replace the import line. So that's it. So import NumPy, you just say import NLCPy. So if you have a Python script using NumPy, I encourage everyone to try it. And so the data transfer between vector host and vector engine, that will be done transparently. You don't have to care about it. And your Python script will be accelerated. And especially if you have large data sets, you shall get the speed up benefit. Now let's get back to the Seismic application. Here I have 3D RTM, reverse time migration performance. And not sure if everyone is aware of Madagascar, but it is an open source software package for multi-dimensional data processing and analysis. It is not only about oil and gas, but it comes with many modules and sample programs related to oil and gas. But with the help of Madagascar, we compared RTM 3D modeling performance with AMD EPIC processor. You can see that the vector machine is 5 times faster than the AMD machine. And if you do some minor tunings, you get another 40% performance increase. So, well, this is one example of the Madagascar or the RTM performance. Actually, I have more results. So more variation, more data size, variation, scalability, and so on. So if you are interested, please contact me. I think, yeah, I can have some discussion with you. And we are also going through FWI, through Waveform Inversion Performance. And here we use an open source program named FWI Mini App. This is only an initial study, and we just compiled and compared the performance. And I'm pretty sure that we can easily make this faster by using compiler paradigmas or modifying a few lines. We haven't done it yet, but yeah, I think I will have some updates shortly. So again, if you are interested, please contact me. I can give you updates and talk about other platforms as well. Okay, so I gave you some examples that we have done so far. Well, actually, some are still ongoing, but there's more and more. So let me highlight some examples which might be some interest of you. The first one is HPC scan from Saudi Aramco. So the giant oil company is interested in vector. They are testing it. Another one is KAUST, and there is a paper from Federal University of Rio de Janeiro about using vector processor for RTM. And I think I touched DGB, Baker Hughes. The last one, CMG, that is about reservoir applications. Well, anyway, the message here is that I am interested to do more and more work here. So if you have other benchmarking opportunities for applications in oil and gas, or it doesn't have to be oil and gas, carbon storage or HPC, everything that requires HPC requirements, please contact me. We can have more detailed discussion, talk what options we have, how we can collaborate, how we can work together, and what would be the next step. I'm very much looking forward to have such kind of discussion. And if you're interested, as a next step, we can do an on-demand hands-on workshop. I can prepare a vector system so that you can access and log in and play around with it. We will have AI machine learning experts on board, and they will help you run programs on vector system. We can prepare sample programs on vector system. We can prepare sample programs so that you can start playing around with it. And of course, not mandatory, but it would be also interesting if you can bring your own program and we can work together to make it run on vector system and see how it performs. So this is something we can offer, and this is something which might be the next step. Okay, so that concludes my talk today. Thank you for your attention. And as I said, I look forward to hearing from you. I'm looking for benchmark opportunities. For if DOE Smart Initiative have any applications that they want to test with vector systems, I would like to do that. So it can be an oil and gas application like RTM, SX-Aurora reservoir, or something else. And as I said, it doesn't have to be oil and gas. It can be CO2 storage, carbon capture, or sequestration. I didn't much talk about CFD today, but computational fluid dynamics. It is well known that vector is good for CFD. So if you have CFD applications, I would be also interested to work together with you. And of course, AI, machine learning. And so basically, vector is good for memory-intensive applications. So if you have such kind of applications, I will be happy to work with you. And you might not be sure if your applications fall in these categories, but in any case, if you can contact me and you see the contact information here, you can contact me by this email, or you can contact to my team with these emails. So I'm looking forward hearing from you, and would like to have some collaboration with you. So that's it. Thank you very much.
Okay, thank you, Ikuta. Appreciate a great talk, a lot of information that you shared with us. So I'd like to open the floor for questions. Any questions? If there is no question, or you're still debating what to ask, I'll have a question of my own. Can you tell us how easy it is to port an existing program or a module to your system, and whether you provide any assistance in this type of porting process?
Okay, so yeah, thank you for the question. So I have to say it depends. It depends how large or how complicated your application is. But in many cases, it's just, and porting is something that you always have to do when you come from one architecture to another architecture. So I think it's pretty same. But as I said, you don't need to use CUDA or OpenSSC, so there is no hurdle here. So in many cases, actually, you just replace the compiler. So maybe if you are using GCC, you just use NCC, which is the NEC compiler. Or if you are using Intel compiler, you just replace it with NEC compiler, and that's it. And of course, you might need to want to do some tuning, but that is a different story. But we do have many tools and mechanisms or methods that will help you do the porting and tuning. So I think that will answer your question.
All right, thank you. Any other questions or comments? Okay, I think there is one question from Sanjay Mamwakar. It says, is there a possibility of making trial runs for reservoir simulation using CMG, GEM, IMEX on your NEC platform?
So we just started to talk with CMG, so I have to confess that it's not ready yet, and we are working on it. So when it's ready, yes, I think I will contact you.
Okay, Sanjay, I guess if you want additional information, maybe you can send an email or have some discussion offline.
Yeah, thank you. I just made a note of his email address, so I'll reach out to Ikuta-san.
Thank you.
Any other question? All right. If there are no other questions, once again, I appreciate the talk, especially since it's about 4 o'clock in the morning Tokyo time. And anyone who wants to look at this is recorded, so anyone who wants to follow up or if you're not attending the meeting or your colleague may want to see the talk, they can go to the recorded version that Terry will upload to the Smart Initiative website or EDX. With that, once again, I appreciate the efforts by Ikuta, as well as appreciate the attendance by everyone in this presentation. So see you next week.
Thank you. Goodbye.
Okay.